Hello, here is an example of a correlation problem being solved on Excel. The problem is this. A researcher explored the relationship between hours of screen time per 24-hour period and hours of quality sleep that night. She predicted that as screen time increased, sleep hours would decrease. Use the 5 steps of hypothesis testing to test the relationship using alpha 0.05. As I mentioned earlier, if you were looking at the examples from last semester, I added a 6th step to it so that people would interpret the finding, and I've removed that step for this semester. So if you see 6 steps written or in an example, you're not responsible for that 6th step this semester. So you'll recall that in these examples, we are having just stipulating population 1 and population 2 as the people we are comparing. So we're comparing people like those in our sample, and you can write this in yours too, in our sample. And we're just comparing them with people who have no relationship between screen time and sleep. There's no relationship between the variables. And what are the variables? Well, the X variable, the one that's listed first, I guess that would be more likely to be causal, is the hours of screen time per 24-hour period. Let's see, is it hours or minutes? Let me look at the data, actually. I guess it's hours. Okay, hours of screen time per 24-hour period. And the Y variable going up to the problem is hours of quality sleep that night. Hours of quality sleep. I think that's adequate. The direction, we can look in the problem for either the word positive or negative, which I don't see in this problem. So then we have to check and see if she predicts directions in either of the variables. And here we can see the researcher predicts that as screen time increase, sleep hours would decrease. And we know that if we have a situation where one variable is predicted to increase as the other decreases, this is a negative relationship. And so a negative relationship would be a one-tailed low test. So let's write that word. Whoops. Well, I'll just still write that it's negative, even though that's not stated in the problem. We inferred that from the directions that were predicted, and so we're looking for a one-tailed low. Our research hypothesis, there will be a significant negative relationship between the variables, and the null hypothesis is the opposite of that. Sorry, there will not be add that word not. Whoops, undo. Oh boy. Let's just type the whole thing over there. There we go. There will not be a significant relationship between the variables. All right, let's continue on to step 2. Create a scatter plot and estimate the relationship. So we're going to estimate the direction once we look at our plot and the strength once we look at our plot. So for this part of the assignment, let's go down to our data. We can see the data, for example, person 1 had 7.1 hours of screen time and 7 hours of sleep. Person 2 had 4.2 hours of screen time and 7.6 hours of sleep, and continuing on down. And so these are the data that we'll plot. I'm going to just slide this over here so we can stay on the line. And we can actually, since we're working in Excel, we don't have to do it by hand. We can select the first column. Note that I'm not selecting the header. I don't think this works well if you select the header, but then you can, once you select these data, then you can hold your Control-Alt key down and select these data. You have to keep the Control-Alt key held down in order to select those 2 columns that are not contiguous. And so then we can go to Insert. We go to this very last chart here, and we can select our very simple scatter plot. And if we look at our data, I'm going to grab this and move it out of the way here. So now we can examine our plot. Here we go. I'm going to close this there. And so now we can give this a name. We can make sure our variables are labeled. We know that we have screen time here. We could do this in Excel. We know that we have sleep over here. Because we're just examining it for a significant correlation, we can draw the line of best fit. It looks like it's going like this. That's not really very good between the points, but we have enough to see that the direction is in fact going down, is negative. And I think these plots, if I had drawn that line better, I think these points are really close to the line. I think this one is really strong. So I think the strength, remember, that can range anywhere from 0 to 1. I think it's going to be close to the 1. I'm going to say this is a 0.85. So my estimate, my R estimate, is going to be approximately 0.85, but I have to remember to put this negative sign, so it's negative 0.85. So let's go ahead and write in the R estimate. I've written it already here in this box, so we could just write our estimate as approximately negative 0.85. Next, we find the cutoff point using alpha, degrees of freedom, and direction. Alpha, if it's not stated, we always use 0.05, but it is stated at 0.05. And so we're going to use 0.05. Alpha equals 0.05. Degrees of freedom is n minus 2, because we calculated 2 means. And if we look down at our data, we can see that we have 13 people in our sample. 13 minus 2 is 11. So let's go ahead, and our direction is one-tailed low. So let's get our calculator tool. We have 11 degrees of freedom with a 0.05. We'll calculate. The critical R value is 0.51. So, and we're going to add a negative sign because we're doing a one-tailed low test. So R alpha, I'll write this a little bigger here, R alpha equals now I forgot, I think it was 0.51. How could I forget so quickly? Yes, 0.51. 2 decimal places is enough, I think. If we need more, we can go back and get them. We might need more if like our sample is really close to this. So let's go ahead right here and draw our little distribution. Remember, when we're drawing the distribution in this test, we're just going to go from 0 to 1. What this is actually representing is so here's the 0. We're just going to put the 1 way up here. We're going to put the negative 1 way down here. Our cutoff point, our alpha, is right in the middle here. So it's 0.51 for this sample size. So let's put R alpha equals 0.51. And we'll go ahead and shade the region in the tail of this distribution. So if we get any score that's further to the extreme than 0.51, we can reject the null. If we get any score that's in here, we fail to reject. And this looks a little bit different because this is actually the plotted R values for a t-test. So that's why this looks a little strange. I don't ask you to do the t-test, but you'll see that your textbook shows you how to do that. I just ask you to look it up. Next, we calculate the R value, and this is where our work comes in. So this is actually what we're referring to, of course, is the sample R value. So let's write that in here. The R value for our sample. So now we go down and we start to do our calculations. And the first thing we have to do is figure out n, which is 13. And our mean, we can calculate just using our average key, equals average, and selecting these data points. To calculate sum of squares, we know, and the step that we're doing now in the end is we're calculating the z-score. The z-score for these individuals, their screen time, and the z-score That shouldn't be listed twice, so let me just delete that. And the z-score for these individuals. Okay, so let's go ahead and calculate the deviations. So deviations, let me write the formula for z up here too before I continue. I'm going to put it right here. Z equals, this is from chapter 4, way back in the beginning, x minus m divided by SD. SD because we're not estimating anything here. We're just calculating the standard deviation using the basic formula. So I'll write these down as we go, but you should know most of them by now. So let's calculate our deviations just as we were doing for the t-tests. Is x minus, and let's click in that m and hit enter. And we find out that 7.1 minus 5.5 is 1.6. That looks good. I want to copy and paste this down. So I'm going to put my $sign in here and enter. And now let's select this and I can just double click right here. So those are our deviations. It wanted to continue onward. So let's just delete that where it says value. And I'm actually gonna reformat that. Another way we could do it if you like formatting as I do is just to copy and drag it down. We know that if we add all these up, they're going to equal 0. So we square our deviations. So let's go ahead and get our deviations squared. And we can just copy and paste that. So I'm just going to copy it and drag it down. And if I right click, I can just paste the function. That'll preserve formatting. You can do it either way. I do not grade you on formatting. And that allows us to sum up this column, which will give us the sum of squares. So let's go ahead and equal sum. Let's get the sum of squares. So 117.86. We're now ready to calculate the variance. Remember, of course, variance is just SS divided by N. We divide by N because we're not estimating. We're using the exact number. So equals SS divided by N. And the standard deviation is the square root of the variance. Okay, and now we're going to do this again. Let's go ahead and get the same thing for these data. The N, once again, is 13. And the mean, we can calculate the average. We could do some copy-paste things here, but I think at this stage of learning, it's likely to maybe cause a mistake. So let's just go ahead and do this manually. Let's calculate our deviations equals each score minus the mean. And we've done that well. We can put our $sign in to make sure that it stabilizes the mean and doesn't move down the column. And so then we can just copy this and paste it down. If we right click and click on this function key, it'll do the calculations without losing our formatting. So just checking up in here, did it do that score minus the mean? It did. And that means that the rest of them are good too. We can square our deviations. If you do decide to use a general copy paste for these problems, I'll caution you to just go back and spot check like this. Place your cursor in the cell and see what Excel actually did for you. And now we're ready to calculate our z-scores. So our zx is just the deviation divided by the standard deviation. And so in other words, we're not going to use this deviation squared anymore. We can kind of cross that off. There we go. We're actually going to take this score. This is our deviation and divide it by the standard deviation. So you might want to literally cross it off because it's really easy to make a mistake of accidentally clicking on deviation squared. So I'm going to erase that box, I guess. Let's go ahead and click on our deviation now. Oops. Equals our deviation divided by our standard deviation. And hit enter. So the z-score for this person is 0.53. The z-score, whoops, for this person is minus 0.431. So that's what we're doing. Now you can see that we could use copy and paste, but we're dividing by a static cell. We need it to stay on the standard deviation cell, but move down to each person's score. So we'll add that $sign. Adding that $sign allows us to copy and paste. And so I'll use this function key to preserve the formatting. I want to keep separate these data, so I guess I want to keep that formatting. And now we can do the same over here. Equals, and I'm going to cross off these deviations squared. Just, whoops, let's get the pen out here and cross off the deviations squared. Let me get rid of all that for a sec here, so I can do this literal cross out. We're not going to use these deviations squared again. We're going to instead focus on the deviations column. So let's take our deviations column and divide by our standard deviation, which we haven't yet calculated. So let's erase that again for a moment. Let's go ahead and get our sum of squares, which is just the sum of the column we just crossed off. So let's see if we can get it here. There we go. There's our sum of squares. Let's get our variance, dividing the sum of squares by n. And let's get our standard deviation, the square root of the variance. And there we go. So now we'll go ahead and we'll get our z-score. We're going to take our deviation right here and divide by our standard deviation. Let's put the $sign in to hold the standard deviation cell static. We'll enter and copy and paste it down. I'll do that function cell again. All right, now we're done. We figured out the z-scores for both sets of data. Now we can figure out our cross products. Zx, Zy is just what it says. The sum of Zx times Zy. So let's go ahead and get that. Here's Zx. We'll multiply it times Zy. We get that very small number, as we might have guessed. There's no need for a $sign now because we want it to go down the Zx column and down the Zy column at the same time. So we can just copy and paste that function in. Next, we can do a couple little calculations. We know the number in our number of pairs is 13, and so our degrees of freedom, remember, is we've already calculated df equals the number of pairs minus 2, because we calculated 2 means, so our df is 11. And next we get the sum of cross products. So we just take the sum of all of these Zx, Zy, or cross products, another word for them. And our R value is taking that and dividing by n. In other words, the R value is the average of all of the cross products. So equals, this is the sum divided by n. And we have an R value of minus 0.9018, minus 0.90. Let's go back up to our problem and fill that in. Our sample equals minus 0.90. By the way, I forgot to write that minus sign in there. It's minus 0.51. Oh, no. Yeah, minus 0.51. And our prediction was minus 0.85. So we did pretty well with our prediction. Here, I think that line got moved somehow. Let's go ahead and draw in our sample score. So here's the 0.51, and here is our actual R value. Our sample equals 0.90. So very much in the reject range. So our decision can be to reject HO. And we can conclude that there is a significant negative relationship between hours of screen time per day, per 24-hour period, I guess, and sleep hours that night. And we can write the statistic. R is the test. Degrees of freedom is 11. Did I get the 11 written in? Equals 11. And we can put that score, 0.90. And then we can put the probability. P is less than 0.05 because that's what we tested at. And that's the end of that problem.